Good day. For this poster presentation, the title is Synthesis of Cesium-lead bromide perovskite nanoparticles under the influence of diphenylphosphine. This is a project that was realized by Eder Castillo, Doctora Fabiola García Gutiérrez, and Dr. Domingo García Gutiérrez. Our institutions are FIME at Universidad Autónoma de Nuevo León, and CIDIT, our research center from Universidad Autónoma de Nuevo León, all in Nuevo León, Mexico. Our contact data is also shown in this slide. Passing on to the contents of this presentation, first we would like to introduce the project, the background of this project, the methodology followed, then the actual research done, that is transmission electron microscopy, X-ray diffraction, optical properties, and then we finish with conclusion, references, and the acknowledgements of this project. Introduction, well, I would like to talk about cesium-lead halide perovskites. These are novel materials that in the nanoscale actually acquire very good optical properties such as high photoluminescence quantum yields, the ability to tune the emission luminescence over the entire visible spectra, and well, in high intensity luminescence and also narrow luminescence that are ideal for electronic applications such as other quantum dot systems. Talking about these other quantum dot systems, it is reported that cesium-lead halide crystallizes by lead seeding, similarly to 2,6 and 4,6 quantum dots. By lead seeding, we mean that actually lead particles are generated in the synthesis that serve as nucleation spots or nucleation agents, nucleation sites that will promote the formation of particles. This could come from ions in the solution, lead ions. And well, if this is actually reported, as this is actually reported, then secondary phosphines used as reducing agents should also improve nucleation during a synthesis, as these secondary phosphines actually reduce lead ions into lead particles in these 2,6, 4,6 quantum dot systems that also synthesized by lead seeding theory. Herein, the effect of diphenylphosphine in the synthesis of nanocesium-lead bromide by the hot injection method was studied. A higher yield of reaction and overall improved final optical properties are expected of this synthesis. So next, the methodology used for this project. First, lead bromide was added to octadecene all in a 3-neck flask under nitrogen atmosphere. We raised the temperature to 120 degrees Celsius, and then after reaching this temperature, we injected oleic acid and oleamine that served as stabilizing agents. Injecting this, we actually dissolved all the reactants we had, leaving out a clear solution. Then we injected cesium oleate, and if the condition needed it, diphenylphosphine, after raising the temperature to 160 degrees Celsius, all again under nitrogen atmosphere. After injecting this precursor of cesium, well, the reaction immediately started. We only left a growth time of 5 seconds before ice quenching into an ice bath. And then we got this clear green solution that is seen in the image. And well, this was taken to the centrifugation procedure where at 9,000 revolutions per minute, 20 minutes, and 10 degrees Celsius. Finally, the residues were discarded and the deposited nanoparticles were used for characterization of this nanomaterial. As for the characterization techniques, we use transmission electron microscopy in bright field mode, high resolution mode, X-ray diffraction for the determination of crystal structure, and finally, spectroscopy techniques such as ultraviolet, visible near spectroscopy, photoluminescence spectroscopy, Fourier transform, infrared spectroscopy. And finally, we determined, we realized a simple stability test all under a UV lamp to see the photoluminescence in real time. Then moving on to the actual time analysis, first seeing by bright field mode in transmission electron microscopy, we could see that the overall nanoparticles were synthesized with a cubic morphology as seen in figure A all had an average diameter of 10 nanometers approximately, where diphenylphosphine had an impact in the size, but well, at high DPP concentrations, we got an average size of 10 nanometers, a stable size distribution also. By checking figure B, we did a high-resolution TEM analysis where we could determine some interplanetary distances relating to cesium lead bromide in monoclinic phase and in orthorhombic phase. We have to remember that the orthorhombic phase is the ambient temperature phase for this compound, and monoclinic comes from the distortion, and other phases of cesium lead bromide also come from the distortion of the lead bromide octaedra that form the unit cell of the perovskite, of this perovskite. So basically this indicates that we have these two phases in the nanoparticle synthesis. Also in figure C, D, E, and F, we could see that these little or small dark particles arise more prominently as DPP was raised in volume. This would indicate, or I mean, these dark particles are related to lead bromide actually decomposing out of the perovskite. I mean, it is growing lead bromide from the decomposition of the cesium lead bromide, indicating that as DPP increases, we have more lead bromide particles in the synthesis. Passing on to electron diffraction, this again in transmission electron microscopy, we could see that we find in the first condition no diphenylphosphine, only orthorhombic phases, just a small monoclinic signal and lead bromide signal. And then as we increase the diphenylphosphine content, we can see that the monoclinic phase actually increases. Intrinsic condition, in the third condition, sorry, we get that even at the trigonal distance, a rhomboedral distance. And then in the final condition, we get more lead bromide signals in electron diffraction, indicating, or evidently indicating that diphenylphosphine is affecting the phase of the cesium lead bromide compound. Then, in order to confirm this, we used X-ray diffraction analysis, and this was actually confirmed by this analysis, as in the first condition, again, no diphenylphosphine. We got only two very narrow peaks of orthorhombic signal and monoclinic signal of cesium lead bromide. Then again, as we increased the diphenylphosphine content, we could see monoclinic intensity rising. In third and fourth condition, we could see rhomboedral signal coming up, and then even in fourth condition, we could see a small lead bromide signal appearing in the diffractogram, indicating again that, well, or I mean confirming that the diphenylphosphine is actually interfering in the phase of cesium lead bromide. This is also evident from peak splitting that could be related to phase transition, and broader peaks seen in these diphenylphosphine nanoparticles. I mean diphenylphosphine cesium lead bromide nanoparticles compared to pristine cesium lead bromide. That in the right is the JCPDS and ICSD cards utilized for the indexing of these peaks. Then moving on to optical properties, for all conditions, we got this characteristic absorption band at 490 nanometers, 488, 489, 485, 492 nanometers. Basically, the common absorbance values for cesium lead bromide. Also, we got a signal at 360 nanometers that is actually related to lead bromide octaedra complexes formed when this perovskite is actually decomposing. So basically, the mechanism is that this octaedra detach from the perovskite lattice and will actually transform either into lead bromide, or this perovskite transforms again into rhombohedral cesium lead bromide. That is the cause for this emission, this absorbance in this spectroscopy. Finally, we have another absorbance peak at 257 nanometers that could be related to lead bromide, pure lead bromide in the synthesis. As for photoluminescence, we have a small quantum confinement from 15 nanometers. We can see that we got a shift to 500 nanometers, 505 nanometers, indicating a quantum confinement. Also, the full width of maxima was 31.1 nanometers. That, well, is quite a large value compared to other reports, but it's still a narrow emission. And, well, all the conditions had this range of full width of maxima from 25 to 30 nanometer. So this is more evidence that cesium lead bromide is actually decomposing into these small complexes and actually forming lead bromide as DPP increases. In order to confirm this, also we made the Fourier transform infrared spectroscopy analysis to see the stabilizing agents signals in the surface of the perovskite nanoparticles. And interestingly, we have these two graphs, A and B. A corresponds to no diphenylphosphine, B corresponds to the highest amount of diphenylphosphine. We could see that the oleic acid signals actually decrease very evidently at the highest amount of diphenylphosphine. And what this could be explained as diphenylphosphine is actually reducing the lead ions in the synthesis. This could only come from the oleic acid complexes before injection. It should be lead olate formed. And, well, this could make oleic acid actually not entirely bound to the perovskite lattice, and thus making a more cesium lead bromide unstable. Also, interestingly, we can see that oleilamine signal actually stayed the same or is more prominent than oleic acid, indicating an oleilamine excess in the synthesis. Again, oleilamine is a catalyst for cesium lead bromide to rhombohedral cesium lead bromide conversion, with this mechanism that I was saying, that where lead bromide octaedra actually detached from the lattice. So this excess of oleilamine is what is causing this signal at 316 nanometer, and could be the cause for the lead bromide nanoparticles arising in this last synthesis condition. Finally, we made a small stability test to confirm this stabilizing agents ratio. And, well, we could see that for the first condition, no diphenylphosphine, we had the most stability, and the photoluminescence actually remained the same as we can see in the image after 21 days. And for 4C, it is evident how the photoluminescence decreased. Also, all particles had turned this yellow color that is related to an increase in size of the nanoparticles. Well, it is because of this improper stabilizing agent ratio in the synthesis. Finally, we measured the mass of these nanoparticles to see if they have actually a bigger yield of synthesis. We could see, as table 1 confirms, that the third condition actually had the highest yield, and it increases from 1C to 3C. And then for C, we had this low yield that could be caused by this interaction with lead bromide that is actually causing not just perovskite, but small lead bromide particles in these more abundant nucleation sites coming from lead seeding. So we can tell that third condition, we had a better stabilizing agent compared to the more nucleation sites generated from lead seeding. And then in 4C, we actually had not a good stabilizing agents ratio. So that's why we had a lower yield of synthesis. As for the photoluminescence quantum yield measured, it was measured with the relative method compared to rhodamine B as the standard. And, well, we can see that the third condition also had very good optical properties, 88% of photoluminescence quantum yield. That is actually a good value, and is in agreement with the literature consulted. So finally, the conclusion, we can say that the highest reaction yield for cesium lead bromide was obtained for the third condition. Cesium lead bromide to rhombohedral cesium lead bromide transition was elucidated, as we confirmed, by this Fourier transform and X-ray diffraction analysis, and is the possible cause for the slightly lower yield for condition, as many more lead bromide particles were generated and could be discarded at centrifugation, or just didn't are less dense than the actual cesium lead bromide nanoparticles. Now improved optical properties were obtained for condition 3C, and the ratio for the stabilizing agents should be improved in order to increase ambient stability in these nanoparticles. That is to say that we could get more diphenylphosphine added to these perovskites, but we just had to establish a better stabilizing agents ratio, so this lead bromide presence doesn't happen or is reduced, and we could get more perovskite particles. These are the references consulted. You can check this if you want to see more about this transition mechanism, this phase transformation, and let's see it in theory. And well, finally, we would like to thank CONACYT support through this project, and Universidad Autónoma de Nuevo León through this project seen in the slide. I would like to acknowledge financial support from CONACYT, and we would like to thank Universidad Autónoma de Nuevo León and FIME for the support, and also all the people involved in this project. Thank you very much for your attention.